So now we'll look at liquid mixtures and see how these rules of thumb or calculations might be changed, and how these concepts of the rule of thumb and the vapor hazard ratio and potential hazard ratio might help us make decisions quickly. The first law to review, and you may have encountered this during your freshman chemistry, but you might have forgotten it. And this is called Raoult's law. And Raoult's law basically says that when you have a mixture, so till now we've been only looking at pure compounds, pure benzene or pure xylene and so on. But if you have a mixture, then the vapor pressure of each specific component in a mixture is reduced proportional to the mole fraction of the component in the mixture. And so piece of A is the vapor pressure of component A in the mixture is equal to XA, which is the mole fraction of component A in the mixture, and P0A, which is the vapor pressure of the pure compound A at 25 degrees Celsius. Let's just work through an example of a mixture where the mixture composition is provided to you. So on the left-hand column, we have the different chemicals in our mixture: toluene, xylene, ethyl acetate, benzene, methylene chloride, and carbon tetrachloride. And you can see the weight percentages in the second column, where we have the highest percentage is toluene, 40%, and the lowest, 2%, is benzene, and everything else in between. And in the third column, we are given the occupational exposure limits for each one of these individual chemicals. In the fourth column, we are given the molecular weights, and in the fifth column, we are given the pure vapor pressure of each one of these compounds. Of course, we need to, as industrial hygienists, develop a level of control that can control exposures to everything in this mixture. And in fact, what we would really like to do is to identify what is known as the controlling component. So which of the components in this mixture is controlling our decision? Which component has the highest potential to exceed its corresponding occupational exposure limit? And so we need to control to manage that, and everything else, all the other components, would automatically be controlled. So let's use our ideas of the vapor hazard ratio in this case to arrive at a decision. So the first four columns, A, B, C, and D, are from the previous slide. And then column E, we can calculate the mole fraction of each component in our mixture. So a mole fraction is essentially the weight percentage, column A, divided by the molecular weight, which is column C. And so these are calculated for each one of the compounds in column E. And then we can find the mole percentage in for each substance, which is column E divided by the total of column E. So we are essentially normalizing it. So the numbers are not too different between column F and column E, because we are essentially dividing, for example, for toluene, we divide 0.434 divided by 1.009. So you get 0.43, which is not that different. But now the different mole percentages add up to 1 or 100%. And then in column G, we calculate the corrected vapor pressure. This is the application of Raoult's law, which basically we are saying that the vapor pressure of each compound in a mixture is reduced by in proportion to its mole fraction. So for toluene, for example, the pure vapor pressure, if we had only toluene, would be given by column D, which is 28.4 millimeters of mercury. But toluene is only 43% in terms of mole fraction. And so the vapor pressure is reduced proportionally. And so the corrected vapor pressure is the mole percentage given by column F and the pure vapor pressure given by column D. So we get to 12.2 millimeters of mercury. And we similarly calculate the corrected vapor pressure for all the other compounds. And then we come to column H, which is the calculation of the vapor hazard ratio, which is the corrected vapor pressure divided by the occupational exposure limit. So we see when you go down this column that toluene is around 0.6, xylene is 0.016, and we come all the way to benzene and suddenly, whoa, it's 4.8. And so even though it is benzene is only 2% of the mixture, it has a very high vapor hazard ratio in comparison to the other chemicals. And if you were to normalize it, and we do that in column I, although that is not really needed, but it just shows the relative magnitude of the effect. So if we make benzene as 100, then toluene is only 12.7 and xylene is 0.34. So benzene really dominates the action here. And even though at first glance, if we were to look at column A, we say, oh, it has benzene is only 2%, so maybe we don't need to worry about it. But in fact, that is the only thing you need to worry about because it is so much more toxic and so much more volatile than any of the other components of this mixture. So if we control for benzene, we would automatically have control for everything else in this mixture. More on this topic on liquid mixtures is given in chapter 25 in a strategy for assessing and managing exposures. And it provides a detailed discussion of the vapor pressure for each component in a mixture and the calculation, the rule of 10 parameters. And Excel spreadsheets are included in your handout materials. And then finally, today, I'm going to talk about why we need rules of thumb and give some examples where these rules of thumb make our decision making fairly quick. Let's consider this scenario, which actually happened to one of my more senior industrial hygiene colleagues who worked in industry for many years. So when he was relatively junior in his career, this happened to him. This plant uses high purity toluene as a solvent in a process that involves 35 workers. And it was 4:30 p.m. on a Friday afternoon. And you, the industrial hygienist, and your family will be leaving on a week-long vacation the next morning, and you want to leave the plant no later than 5 p.m., and you have another 3 or 4 items on your task list that have to be completed before you leave. And right then, this process engineer comes into your office and asks you to sign off on using a lower grade of toluene that contains up to 1% benzene. And if we use this lower grade of toluene, that'll save the plant about $250,000 a year. And the operations department has already concluded that, at least for the industrial purpose, the lower grade toluene is acceptable. And the safety and environmental departments have already signed off on the change as well. But the process engineer indicates that he realizes the OSHA standard communication and benzene standards will require some new labels. The workers will have to be trained, and these requirements will need to be completed prior to receiving the new material. And the plant will need to order a new shipment no later than Saturday. What do you think as industrial hygienist? Can we do this? And here are some pieces of information that you have in your capacity as industrial hygienist for this plant. Toluene is monitored bi-monthly, and the data collected over the last year indicates that the exposure is roughly 9.5 parts per million, 95th percentile. Toluene has a threshold limit value of 20 parts per million. We know its boiling point, we know its vapor pressure, we know its molecular weight. And we also know the same pieces of information for benzene. So do you want to sign off on the change? So as an industrial hygienist, you don't have the luxury of actually going and measuring people's exposures because the change hasn't yet happened. But you can use your knowledge of the vapor hazard ratio. So the vapor hazard ratio for toluene is 28.4 millimeters of mercury divided by 20 parts per million occupational exposure limit. So the vapor hazard ratio comes to 1.42. The vapor hazard ratio of benzene can similarly be calculated, but now you have to use Raoult's law because it's just 1% of benzene and in a mixture of toluene and benzene. And so we can calculate, although I'm not going to show you the calculation for the vapor hazard ratio for benzene, but basically it's similar to the calculation I showed you for the mixture earlier. And so the vapor hazard ratio for benzene is 1.12 millimeters of mercury, which is the reduced or corrected vapor pressure for benzene in a mixture, divided by its occupational exposure limit of 0.5 parts per million. And so the vapor hazard ratio is 2.24. As you can see from the bullet on the very top, the vapor hazard ratio for toluene is less than the vapor hazard ratio for benzene, 1.42 versus 2.24. And the ratio of the vapor hazard ratios for benzene to toluene is 1.58. The toluene exposures are at 9.5 parts per million, the 95th percentile. And so it is roughly 47.5% of the occupational exposure limit. The benzene exposures are therefore going to be 1.58, which is the ratio of the vapor hazard ratios, times 47.5% of its corresponding OEL of 0.5 parts per million. And so the benzene exposures are 1.58 times 0.475 times 0.5. So you get an expected benzene exposure 95th percentile as 0.38 parts per million. So this value is below the benzene threshold limit value, and but it is above the action limit, which usually triggers medical surveillance requirements. And therefore, my colleague basically said that it would be my recommendation as an industrial hygienist to not approve the use of toluene with 1% benzene. And the reasoning that my colleague provided was it's a known human carcinogen and it will be introduced into a workplace where a significant number of employees will be affected at a significant level of exposure, and there would likely be a series of other costs that would have a negative impact on the projected savings. So this is an example where a simple rule such as this vapor hazard ratio can be used along with already existing data to arrive at a decision quickly. And as you can see in this case, it is a decision with significant dollar value attached to it. And this is the sort of decision that a plant manager might expect from the industrial hygienist from time to time. And even though in this case, everybody else at the plant had signed off on this proposed change, the industrial hygienist brings his or her expertise and says, nope, this is not a good change because it will affect worker health adversely. In summary, today we looked at three different rules of thumb that allow relatively rapid decision making with great degree of confidence, and it provides the basis for initial exposure assessment in the AIHA exposure assessment strategy. As the name suggests, rules of thumb are just that. They are quick and dirty ways of assessing exposures as a first step. They are not the end of the process, and this is just the beginning of the process of assessing exposures, and they can be used when you are hard up on time, you have to arrive at a decision quickly, Or, like I said, you can arrive at a preliminary decision. But this needs to be followed with actual measurements that either validate or don't validate your initial assessment. And in your course materials, I also provided an Excel spreadsheet that I will go over in a separate unit and describe its use. And you will be using this as a homework assignment to assess 10 different exposure scenarios using just the rules of thumb.